Our next item on the main menu is Rheological curve fitting. We use these curve fitting tools to analyze our experimental data and determine various rheological parameters. As we press the Rheological curve fitting button, it takes us to the curve fitting submenu. We see that there are three items in this submenu. The first one is to fit viscosity versus shear rate data. The second one is for fitting shear stress versus shear rate data. And the third one is to fit viscosity versus temperature data. So let us take a look at the first item on this submenu. As we press this button, it takes us to the viscosity curve fitting screen. On this viscosity curve fitting screen, we enter our experimental data and then fit them to various viscosity models such as Cross model, Karo model, or Karo-Yasuda model. For more details on these models, please refer to the help screen. In this free version of this app, we can enter our data manually only by entering data points one by one using the keyboard. Note that in the Pro version, you can also load the data points from a text file or scan the data points directly from a QR code or a data matrix image. We first press the manual button and then enter the shear rate and the viscosity and press enter. We keep repeating this until all our shear rate versus viscosity data points are entered. There is also a demo button by which you can load some example data points so that you can try the curve fitting functions before entering your actual experimental results. As we press the demo button, we see that it has loaded 26 shear rate versus viscosity data points. Now that these data are in place, we can press the plot button to see how the viscosity curve looks on the graph. We can now use either the Cross or the Karo or the Karo-Yasuda model to analyze the data. Let us try the Cross model. As we press the button, we see the curve fitting results, giving us the zero shear viscosity or eta 0, shear thinning index or N, critical stress or tau star, and the relaxation time or lambda. It also indicates the total number of data points used in this analysis, the number of iterative steps it took to reach to the solution, and the relative error and the R-squared value. Once we have fitted the data, we can again use the plot button. This time, it will not only show the data points, but also the fitted model as a continuous line, so you can see the extent of the fit. Once we have used the demo, we are now ready to enter some real data. Let us first clear the board, press the manual button, and start entering some data points. We have now finished entering all the 16 data points from our rheology experiment. To look at the data graphically, we press Plot. We can see that the graph suggests the presence of a zero shear viscosity at low shear rates and a shear thinning behavior at high shear rates. We also notice that there is some scattering in the data at the low shear rates, which is not uncommon in rheology experiments. Let us choose an appropriate model that can describe such a behavior. In this case, we can choose the Karo-Yasuda model. As we press the button, it gives the model fitting results, predicting a zero shear viscosity of 51.69 pascal second, a shear thinning index of 0.146, a tau star of 200 pascal, a relaxation time of 0.258 seconds, and a Karo-Yasuda constant of 0.668. The overall relative error for this model fitting was 5.73%. As we press the plot button again, we can graphically examine how the model fitted the experimental data. We can see that in this case, the model, represented by the solid line, fitted the data quite nicely. Please note that if you use the Pro version of this app, you can also save the data as a text file and reuse later if you want to do any reanalysis. Our next item on the curve fitting submenu is flow curve fitting. We use this function to analyze the behavior of complex fluids and determine their non-Newtonian flow characteristics such as yield stress and shear thinning index. Let us have a look at some experimental flow curve data. Here we have entered our shear rate versus shear stress results using the manual data entry function. When we look at the graph by pressing the plot button, it becomes clear to us that it is a yield stress material as we see a finite, non-zero shear stress at very low shear rates. So we decide that we will try one of the yield stress models, either the Bingham plastic or the Herschel-Bulkley or the Casson model, and we see that the Herschel-Bulkley model gives the minimum absolute error. Based on this observation, we finally choose the Herschel-Bulkley model and we get a yield stress of 8.15 Pascal, a consistency factor of 5.6 SI units, and a shear thinning index of 0.483. And the fitted model looks like this on the graph, nicely passing through all the scattered data points. Our next item on the curve fitting submenu is temperature curve fitting. Using this function, we analyze how the viscosity of a material changes with temperature and fit that trend to either the Arrhenius or the WLF model. Here we have entered the experimental results of a liquid's viscosity versus its temperature. We can see that as expected, the viscosity decreased as the temperature increased. Before we use one of the models, we need to specify a reference temperature. The viscosity at the reference temperature will be the reference viscosity, based on which the models will predict the viscosities at other temperatures. By default, the temperature from the first data point will be the reference temperature. However, you can change it by using the temperature value from any other data point. For example, here we will use the temperature from the third data point as our reference, which is 35 degrees Celsius. Let us now try the Arrhenius model. As we press the button, the model predicts an activation energy or EA as 28.071 kJ per mole. Looking at the graph now, we see that we have a reasonable fit, so we can accept this analysis result. Please note that when you are doing a temperature curve fitting, your choice of the model should be based on the type of the material. For a liquid without a TG, or if the TG is well below the experimental temperature range, we normally use the Arrhenius model. However, for glassy liquids or amorphous polymer melts, where the temperature is not more than 100 degrees Celsius above its TG, the WLF model may be used.